year. Velocity saturation is one of the short channel effect. Other short channel effects are also shown here. These all are short channel effects or secondary effect of MOSFET, and few of them we have already discussed, that is CLM, channeling modulation, we have discussed, and also we have said about SCI to some extent, hot carrier injection. Then others are DIBL, brain induced barial lowering, SCBE, substrate current induced body effect, then velocity saturation and mobility degradation. This velocity saturation and mobility degradation we are going to discuss now, because that is the topic coming in the main slide, which is based on Rabe. Mobility is what? Mobility mu describes the age with which carriers drift in the channel, rather surface of substrate material. It is defined by average carrier drift velocity dvd divided by electric field. Mu is the mobility, or in other words, you can also say that drift velocity, you can also write that drift velocity Vd is proportional to electrical field E. Sometimes we write Ex also, because this drift velocity is in the parallel or lateral field, that is because of the VDS, and this mu is considered as proportionality constant. Okay, so this mu is nothing but the age with which carriers, that carriers may be hole or electrons. If it is electron, then we write mu n. If it is hole, then we write mu p. And its unit is centimeter square per volt second. If it is given as centimeter per second, and electric field is given as volt per centimeter. So here we are going to discuss what happens to mobility with change in doping concentration as well as temperature. The mobility may vary in a number of ways. Primarily, it varies according to the type of charge carrier. Mu n versus mu p. If you consider, then mu n is 2 to 3 times larger than mu p. At low temperatures, the mobility is higher, but is a strong function of doping concentration, Na or Nd. Na in case of the substrate of N MOSFET, and Nd for the case of P MOSFET, substrate of or well of P MOSFET, N well of P MOSFET. So as it becomes more limited by impurity scattering, at low temperature, the mobility is limited by impurity scattering, whereas in high temperature, it is limited by lattice scattering. That is, the mobility decreases with increasing doping concentration, that we'll see in one plot, due to the impurity scattering. At high temperatures, mobility tends to be limited by lattice scattering, and it is proportional to T to the power minus 3 by 2, and relatively insensitive to the doping concentration. Impact of temperature variation on mobility becomes less pronounced as doping density increases. These are the various statements regarding mobility, doping concentration, and temperature. and how they are affected at different temperature, impact of scattering, impurity scattering at low temperature, and at high temperature lattice scattering dominates. Here you can see in this diagram the electrons mobility and hole mobility is shown. It is almost 2 to 3 times higher. Electron mobility mu n and hole mobility mu p are difference even at same doping concentration. Here in this plot, doping concentration has been varied or rather increased from 10 to the 14 to 10 to the 20, and how the mobility decreasing, that is shown. Once doping concentration is increased, the impurity scattering becomes dominant, and due to frequent scattering in the channel, the carrier moves slowly rather. Okay, so mobility is decreased. If you read this first bullet, it is saying is the bulk mobility. This is the case of bulk mobility. Bulk mobility means bulk. If I draw a MOSFET structure, and you have the substrate or body, we are concerned about the mobility of carrier in the surface or in the channel where inversion layer is formed. Whereas this mobility is talking about this mobility is further area, in this area, and in further area of the substrate mobility is higher. What is shown in this figure 2.8 is the bulk mobility applicable to conduction in silicon substrates far from the surface. This is the surface. In the inversion layer of a MOSFET device, the current flow is governed by the surface mobility, means channel mobility, which is much lower than the bulk mobility. This you have to understand. This is mainly due to the additional mechanism between the carriers and SiSO2 interface. Where is the interface? It is talking about this interface. SiO2 is this one, and Si is this one. P-type Si in this case. If I make a N MOSFET, then it is a P-type substrate. In the interface, you will have the imperfection in the covalent bond. You have in this bulk material perfect covalent bond, whereas in this you have the silicon dioxide. So covalent bond imperfection are found here, defects are there. So due to that defects, electrons are trapped or carriers are trapped and then released. That is the reason the mobility decreases compared to the bulk mobility. Now, another statement here given is surface scattering decreases with electric field. Here, effect of electric field is less in the deep or far further area of the substrate. As I said earlier, that substrate may be 500 micrometer thick, whereas the devices are fabricated here on the surface at around 1 micrometer thickness. All are just providing the mechanical support to the device. Now, one thing I want to say, because and the at the end it is said that mobility decreases with electric field, and electric field works here in this region mainly. What are the electric fields required for the MOSFETs to operate are here. We need two electrical field. One is vertical, another one is horizontal. Vertical field is due to the gate to source voltage VGS, and horizontal field is due to the VDS, gate to drain to source voltage VDS. And since it is vertical, we have denoted it with EY equals to VGS by TOX. Remember that electrical field is what? Electrical field between 2 points having potential difference of V and distance of D between these 2 points is nothing but V by D. Electrical field is this. So oxide thickness is the distance of from this VGS and this point, whereas horizontal field is between VDS, I mean drain to source, and distance is L. So EX is written as horizontal field, and which is nothing but VDS by L. Could you understand? Ashan, Ashan, and that boy is there.
Yes, sir.
Harsh Tripathi, are you there? Harsh Tripathi is still absent. No. Shashank, are you there?
Yes, sir.
Are you getting that two kind of electrical field works on a
Yes, sir.
MOSFET? Now, impact of high electric field on drift velocity we'll discuss. In this plot, you can see we already know that VD is proportional to E, electrical field. Proportionality constant is mu. So it should linearly increase at a 45-degree angle, for example, should be. But after the electrical field reaches certain value, say EC, here it is written 1.5, the carrier is not able to cope up with the electrical field. It is going to saturate the drift velocity. Velocity of the carrier is saturating at this field. Vd sat equals to 10 to the power 5. So at higher field, but why the higher field is going to occur, that also we'll see. Ideally, it should go like this. As you increase the field, it should keep on increasing. But no. When field is reaching certain critical value, the drift velocity is saturated. And in nanoscale device, ID tends to saturate very quickly as VDS increases. Normally, this field actually we are considering the EX or horizontal field due to VDS. And we know that pinch off occurs when VDS is greater than equals to VGS minus VT. This is applicable for the long channel MOSFET. But in short channel MOSFET, before this condition happens, the saturation may occur in the current because of the saturation of the drift velocity. VD sat, we can write VD, VD sat. This is VD sat is drift velocity, saturation drift velocity of the carrier. Okay, it is not VDS or SAT or something like that. It is not that. Drain to source voltage saturation. No, we are talking about the saturation drip velocity. It may occur even before actually saturation is appearing due to the condition, this condition in saturation region. The assumption that the saturation occurs at pinch off point is no longer correct in short channel MOSFET. Saturation at DSM, deep submicron devices, occurs when the carriers reach velocity saturation. That is, when they reach the speed limit of the carriers in silicon. Understood? What is velocity saturation?
Yes, sir.
Pinch off should occur at VDS greater than equals to VGS minus VT, but before that it may happen. Current of the MOSFET can saturate even before that due to velocity saturation of carrier. Now, what is the scenario of field, vertical as well as horizontal, that we are going to see? As can be seen, horizontal field has increased over the years. In 1980, EX was 5 volt by 5 micrometer. Oxide thickness was 5 micrometer. And it gives you 10 to the power 4 volt per centimeter electrical field, horizontal electrical field. In 95, it is this much. And if you look at 2005, it is this much. Because oxide supply voltage has become 1 volt. It has been reduced from 5 volt to 1 volt, and oxide thickness has become 0.065 micrometer, that is 65 nanometer. Is it 65 nanometer? 0.065 micrometer. If you divide it, you get this value, and it is 150 times compared to the 1980s value. If you take this value and this value, the 150 times increment has occurred in the horizontal electrical field. It is huge electrical field is occurring, and that's the reason the velocity saturation is occurring. And if you see here, vertical electrical field, that is due to VGS, and it is related to oxide thickness. See that it was 100 nanometer, 1000 into 10 to the power minus 10 means 100 nanometer earlier. Whereas the calculation gives you 15 to the power 4 volt per centimeter. Here if you come, it is 1.0 volt divided by 12 to the power minus 10. It is 1.1 nanometer, I think. This is what in nanometer, how much it is? 0.065 micrometer. So it is how much? In nanometer, it is how much? Shashank?
65 nanometer.
65 nanometer. It is what? It is L. In 2005, say, channel length has been considered to be 65 nanometer. Whereas oxide thickness in 2005, it is 1.2 nanometer. Earlier it was 100 nanometer in 1980. So if you consider these values and compare, you will see that 16.6 time increment has occurred in the vertical field. We have already discussed the scaling theory proposed by Leonard long back in early 70s, but that theory, I mean, his theory has not been followed in the same way. That his scaling factor was 5, K was 5, whereas industry uses what? What is the scaling factor
Root 2.
industry? Huh?
Square root of 2.
Square root of 2. So even though scaling has been done vertically as well as horizontally, vertically means the oxide thickness has been reduced, and horizontally channel length has been reduced, but still there is a gap. The same proportionate way in not in the same proportionate way it has been done. The way supply voltage also should have been done. So it could not be done. So how much supply voltage or because threshold voltage is also a matter. If threshold voltage is too less, then also a problem. Substrate leakage current will be there. So from here we can understand that what is happening in a new device. Why electrical field is so high, and because of that velocity saturation is occurring. What you see in this plot is the electric field versus carrier velocity. At high fields, the average carrier energy increases, and carriers lose their energy by optical phonon emission nearly as fast as they gain it from the field. This results in a decrease of the mobility as the field increases until finally the drift velocity reaches a value of Vsat. Vsat is the saturation drift velocity, 10 to the power 7 centimeter per second. This phenomenon is called the velocity saturation. In this figure, it shows the measured field velocity field relationship of the electrons and holes in high purity bulk silicon. High purity may be intrinsic silicon at room temperature. At low fields, the drift velocity is proportional to the field at 45 degree slope. In the previous diagram, I was telling that 45 degree, it should be ideally 45 degree angle. In 45 degree angle, it should increase. But it is, see, at low field, it is there, this one, as you can see. But after that, at field is increasing, it is gradually saturating. So this is what velocity saturation and carrier mobility degradation, you can say. The effect of the vertical field on mobility can be modeled to first order as follows. Effective mobility, if you consider the vertical field, this gives you the vertical field. VGS minus VT is the effective voltage divided by the torques. That is what the vertical field. So this may be your nominal mobility of a MOSFET at the presence of low field. Field is not so high. Its value may be around this 540 centimeters square per volt second. So what we see here in this expression is that the mobility, this 1 plus something, eta is the empirical values or parameter, and theta and eta are empirical parameters or fitting parameters. So we see that the low field mobility, whatever is, it gets reduced due to the vertical field. 1 plus something, some value. So ultimately, the quantity here will be reduced. Could you understand, Prajwal?
Sir, how will vertical field influence the mobility when the mobility is in horizontal direction?
See, carrier is moving, right? Carrier is going to move in the channel in this direction. Suppose you have the n plus in this side, n plus in this side, right? We are talking about in MOSFET. And carrier is moving in the channel in this direction. Gate is here, source and drain. In this direction, carrier is moving. And this field, since it is electrons, the positive charge is there, right? This positive charge is trying to attract in this direction or not. So two force actually acting on these electrons, and its effect is retarding. Moreover, here in the interface we have discussed that there is a imperfections in the bond. Imperfections, then defects are there because one material is SiO2, another one is Si. So perfect covalent bond will be in the further area, but not in the interface. So those interface also traps. Okay, and moreover, this electrical field is pulling up, and this vertical horizontal field is pulling in the horizontal direction. Effect of that is there. Due to that effect, the horizontal field is going to reduce the mobility of the carrier. Are you getting? Ideally, it should trip velocity should be like this at low field, but it doesn't happen at very high field because one field is trying to pull up towards it, towards the gate. Okay, so effect of that is causing to reduce the mobility of the carrier. Is it understood?
Yes, sir.
We should first include the effect of vertical field by using this equation, and then we got this one effective. Mu E is the effective, and we have seen in this equation that actual value which is at low field that will get reduced by this equation. So for computation of BD, drift velocity, first you have to consider the vertical electrical field that will reduce the mobility, will get the mu E. Then you find out the drift velocity with this equation. To account for the horizontal field, we can express drift velocity Vd as a function of horizontal electrical field Ex. That is, Ex is the field, horizontal electrical field, and EC critical electrical field. I mean, Ex you are increasing, and at certain point when Ex will be high enough, the carriers will start saturating, and drift velocity will not increase linearly with the field. So for this is, I mean, applicable for Ex less than EC, and this is applicable for Ex greater than EC, where EC is the critical field and BD sat, the drift saturation drift velocity. Take, one call is coming. I'll take this call and hello, saturation drift velocity, and when it is EC or sorry EX is greater than equals to EC or critical electrical field. If you put EC equals to AC means that value, then we get EC equals to 2 divided by E. So this sets up the relationship between EC and VDSAT. So with this, I want to go back to our original slide, leaving behind this. It is same thing what we were discussing earlier, that drift velocity initially at low field it increases linearly, but afterwards when EC reaches, then the velocity of the carrier saturates.
So then this effect is only in short channel MOSFET?
What is that? Repeat, please.
Is this effect only in short channel MOSFET?
Yes, short channel MOSFET. Nowadays, MOSFETs are very small, even less than 20 nanometer, whereas earlier it was 20,000 nanometers. So during those days, these effects were not pronounced. It was negligible. It was negligible earlier. And today's MOSFET is the things what we are going to deal with, because all chips are made with these MOSFETs, shorter MOSFETs. Okay, so here some data is given for p-type silicon. The critical field at which the electron saturation occurs is 1.5 × 10⁶ volt per meter or 1.5 volt per mm, and saturation velocity approximates equal, 10⁵ meter per second. Actually, this is 10⁵ meter per second. This means that in an NMOS device with a channel length of 1 mm, only a couple of volts between drain and source are needed to reach this saturation. And we have seen in the previous discussion that it has increased 16.6 times increase the horizontal field. Vertical field is more than 150 times. So velocity saturation is causing saturation of current in. This is all what we just now discussed. This equation also we have seen a relationship between critical electrical field and drift velocity, saturation drift velocity. It is 2 Vsat by mu. This is all you remember for the exam purposes. And this equation also we have seen. And putting the value of this thing, velocity saturation, K is the measure of degree of velocity saturation. K is given by 1 by 1 plus VDS, V by ECL. V here it is nothing but VDS, drain to source voltage, and L is the distance between that. It is nothing but EX. Try to understand. This VDS by L is nothing but EX. Putting the value of K in this equation of what? This is linear region equation of current. From here to here, it is linear region current equation. If you put here the K, which is dependent on VDS, and K value of K is less than 1. If it is 1, obviously it is going to be the same equation of long channel MOSFET. In a short channel MOSFET, to take into account the velocity saturation of the carrier, you have to add this term with the original long channel MOSFET current equation. and K is given as 1 by 1 plus Ex by L, basically it is. That is Vds by L. Vds by L is going to be Ex, and Ex is the critical electrical field. So this value is always less than 1. And hence, what will happen to the current? Current delivered by this small short channel device will be smaller. Okay. As you can see at the last line, it is written for short channel devices, K is smaller than 1. Okay, which means that the delivered current is smaller than what would be normally expected. This is what main theme of this velocity saturation. Same ID sat is written, putting the value of B sat. You know, B sat we have seen how it is related with the electrical field in the previous slides. For the short channel devices, K is smaller than 1 and VDSAT is lower while taking velocity saturation to consider. VDSAT is what? This VDSAT is the saturation at which saturation is going to occur in the current. VDS is the VDSAT saturation orient voltage between drain and source. So at lower VDSAT is lower while taking the velocity saturation into account. Otherwise, normally saturation occur at higher voltage, drain to source voltage. That is VDS greater than or equals to VGS minus VT, which was earlier for long channel MOSFET. So due to this, it is going to decrease. Here we have we can see that ID versus VDS plot is given for long channel MOSFET and short channel MOSFET. See, saturation occurs due to the channel pinch off at VDS greater than or equals to VGS in this case. Whereas in a short channel MOSFET, saturation occurs due to velocity saturation of charge carriers at less than pinch off VDS. And here it is saturating. And another thing is that it is not saturating and it is not getting parallel with the x-axis. Still, it is almost linearly increasing with VDS. And that is because of what? Can you say another effect is there? Short channel effect. What is that?
CLM.
CLM. Very good. So due to CLM also, so CLM, velocity saturation or mobility degradation, these are all the short channel effects and are characteristic of the short channel MOSFETs. See what is given here, extended saturation region. See, it is not really fully saturating. Okay, whereas in this case, long channel MOSFET, it is not happening. It is saturating immediately, and it is taking longer time due to CLM and velocity saturation. This all we have discussed. To capture the CLM, we have to add another term 1 plus lambda VTS with the current equation, and we have also written this equation and described also, proved also, or derived also. That is beta by 2 into BGS minus VT whole square into 1 plus lambda VDS was the equation where beta equals to mu n C ox W by L. This all we have discussed, CLM. So mobility degradation, what is we have discussed, and hence we go ahead. This all we have seen. This also electrical field This is just seen, so we'll go ahead and see this relationship. You remember for the exams. Here, what we try to understand from these plots, let us see the behavior for the NMOS transistor in the different region is best understood by analyzing ID VDS plots. Which plot ID versus VDS with VGS as parameters. For different VGS, like VGS equals to 1, 1.5, 2, and 2.5, it has been plotted. And we see that quadratic dependence is there here. See, the distance between this and this and this and this is not same. Here, linear dependence is there. Here, more or less, we see that distance are not much difference, or everywhere almost same, whereas it is quite different from this. This is indicating that the velocity saturation effect is there. We would expect device to display identical velocity characteristics. The main difference, however, is that the first device has a long channel LD equals to this, while the second device is having LD, means channel length 0.25 micrometer, and experiences velocity saturation. Consider the first long channel device. In resistive region, the transistor behaves like a voltage controlled resistor, as 45-degree angle is there and current is increasing in 45-degree angle. While in the saturation region, it acts as voltage controlled current source, means current is saturating fully when the channel length modulation effect is ignored. The transition between both region is separated by this expression VDS equals to BS minus VT, means somewhere here. Here, this is the point. The square dependence, that is quadratic dependence, as a function of VGS in the saturation region, typical value for long channel device is clearly observable from the space between the different curves. The linear dependence of the saturation current with respect to VGS is apparent in the short channel device. This is what I was telling. These differences are all same. Linear dependencies. From one VGS to another voltage VGS, you are changing, is happening. Whereas you see here, it is not. Quadratic dependence is visible from this plot also. Notice also how velocity saturation curves causes the device to saturate for substantially smaller values of VDS. Smaller values of VDS. This results in a substantial drop in current drive for high voltage levels. For instance, see the values VGS equals to 2.5 volt, VDS equals to 5 here at this point. At this point, for example, VGS equals 2.5 volt and VDS, this point actually, 2.5 volt. And value of current is 540 milliampere. This is 10 to the power minus 4. Okay, so it is 540 milliampere. And whereas at 2.5 volt VDS and VGS equals to 2.5 volt, see, if you see the current, it is 220 milliampere. So this can be concluded that velocity saturation has reduced the current ID. of the device. Are you understanding? If you see the ID VGS plot of long channel MOSFET and short channel MOSFET. This is long channel, this is short channel MOSFET. See that this portion is entirely quadratic, whereas this is linear, almost linear it is. It is clear. A quadratic versus linear dependence is apparent for larger values of VGS. This is also the effect of velocity saturation. If you consider the P MOSFET, it will be same. All the derived equations hold for the PMOS transistor as well. The only difference is that for PMOS devices, the polarities of all voltages and currents are reversed. This is illustrated in this figure, which plots IDVDS characteristic of minimum size PMOS transistor. We have also discussed by drawing the structure of PMOSFETs and carrier in that PMOSFET is whole, that also we have discussed, isn't it? Rajwal, can you remember?
Yes, sir. Which one, sir?
The PMOSFET also one day we discussed. After drawing the structure, if you apply voltage at the gate, 0 voltage, then how it is the voltage is affecting the channel region. In MOSFET, the channel is formed with electrons. Inversion layer is of electrons, whereas in PMOSFET it is with hole. That we discussed or not? Can anybody say? Are you remember?
Yes, sir. We discussed.
Yes, sir.
We discussed. Okay. Here in this plot, what is telling interesting thing is what? Interesting to observe is also that the effects of electric saturation are less pronounced compared to NMOSFET. Here, effect of velocity saturation is less. Why? This is attributed to the higher value of critical electrical field resulting from the smaller mobility of the holes. We have said today only that mu n is greater than mu p by 2 to 3 times, and we have seen the plot also of mobility. Okay, so due to smaller mobility of hole, the saturation occurs at higher electrical field in holes. So impact of saturation, velocity saturation is less pronounced in P MOSFET. It occurs but at higher electrical field because of lower mobility of the hole. Now, next thing is subthreshold conduction. We have already discussed subthreshold conduction. So here, summarized version you can see. Current does not drop abruptly to 0 at VGS equals to VT or VGS when VGS is less than VT. It is not. Most transistors partially conduct when VGS less than VT, and transition from on to off is not abrupt, but it is gradual. In a log plot we have seen. This also we have seen how VT is here and it is not zero current. It is not falling to 0 here. Still gradually current, you see, gradual drop is there, and we have defined also the sharp threshold slope. And earlier we have written eta. This symbol was eta, and this equation also we have seen with VGS minus VT, but here only VGS is written. Remember that the device modeling is done with different resources, and for a single thing you will get various equations. So it is not unexpected that VGS is not written, but mostly VGS plus VT equation will be always available in the literature. So we want MOSFET to be an ideal switch for digital application, but it does not behave ideally because I shape still flows when VGS is less than VT. We expect ID should drop as fast as possible when VGS falls below VT. The inverse rate of decline of current with respect to VGS below VT hence is a quality measure of device. And these are all discussed earlier while discussing the sub-threshold current equation, etc. For an ideal MOSFET, we have seen that VGS, S Shabda slope is 60 millivolt per decade at 300 K or room temperature, and ISAP drops by a factor of 10 for a reduction of VGS of 60 millivolt. It means this only. Okay, for actual FETs, of course, it is 90 millivolt per decade. That is eta equals to 1.5. Here, ISAB has some important indirect consequence. Direct consequence is what? There will be leakage and battery will be exhausted very frequently without any computation. Battery of any battery operated devices will be dropped. Battery will be consumed. Generally, ISAB to be as close as possible to zero. VGS, when VGS is zero, then I sub should be zero. That is expected, but it doesn't happen. It is important in case of dynamic circuits which rely on the storage of charge on a capacitor. Hence, its operation can be severely degraded. Dynamic circuit is not known to you. Is it known? Section A student or B student? Have I discussed what is dynamic circuit?
No, sir.
Okay, dynamic circuit is this is a dynamic inverter. Static inverter you know, but dynamic inverter you don't know. So here onwards we'll discuss in the next class because I have to take another class. Because dynamic circuit has come, I have to discuss it. So it is better to discuss in the next class. Okay, then leave the class and take other classes.